First Law of Thermodynamics, ChemQuest 53 by Andrew Lee. The first law of thermodynamics states that the change in internal energy of a system equals the sum of the heat and the work. And the internal energy of a system can change. If the system gains heat, then the internal energy of the system increases. If the system loses heat, then the internal energy of the system decreases. If a system does work, then the internal energy of the system decreases. If work is done on the system, then the internal energy of the system increases. So here are some critical thinking questions. For each of the following, state the system and whether the internal energy increases or decreases. Number 1. Lifting a ball from the ground and holding it 6 feet above the ground. The system is the ball and the internal energy increases because work is being done on the system. 2. Heating up a piece of pizza in the microwave. The system is the pizza and the internal energy increases because the system gains heat. 3. An ice cube is melting while it sits on the kitchen counter. The system is the ice cube and the internal energy decreases because the system loses heat. 4. Two molecules bond together and heat energy is released. The system is the two molecules and the internal energy decreases because the system loses heat. Enthalpy is a heat energy involved in a chemical reaction. The change in heat energy is called the change in enthalpy and given the symbol delta H and is measured in kilojoules. Here are some examples of how change in enthalpy is written. You have the reaction and next to it is a delta H and its value. Enthalpy can be described in two ways, endothermic and exothermic. Endothermic means the system absorbs energy from the surroundings in the form of heat, and exothermic means the system releases energy usually in the form of heat. For endothermic, the change in enthalpy is positive, and for exothermic, the change in enthalpy is negative. When one substance is made up from elements in their standard states, the enthalpy change is called the enthalpy of formation and is represented by a symbol of delta HF. Here are two examples of what it looks like. You can solve for the enthalpy of a reaction by knowing the enthalpy of formation for each substance. To solve for the change in enthalpy of a reaction, you take the sum of the moles times the product's enthalpy of formation minus the sum of the moles times the reactant's enthalpy of formation. For example, you have the following reaction and their enthalpy of formation. You look at the products first and take 2, the number of moles, and multiply it by the enthalpy of formation of H2S, and add it to the enthalpy of formation of CO2. Then you do the same thing for the reactants. 2 times the enthalpy of formation of CS2 plus the enthalpy of formation of H2O. Then you do products minus reactants and you get negative 66.9 kilojoules. Remember, delta HF is used for enthalpy of formation and delta H is used when you solve for a change in enthalpy. Here's another example problem. Using a table for standard enthalpies of formation, you get the following values and then you just take the sum of the moles times the product's delta H minus the sum of the moles times the reactant's delta H, and then you get negative 91.4 kilojoules. Here are some more practice problems. All the enthalpy of formations were found using a table of standard enthalpies. But let's look at problem C. As you can see in the reactant side, CH4 has a delta HF of negative 74.87 kilojoules, but the delta HF of Cl2 is 0. It is 0 because Cl2 is in its natural state and not formed. The delta HF is also 0 for O2, Na, Mg, and other substances that are in a natural state and are not formed. Using only the information given, how can you calculate the change in enthalpy for reaction C? By adding the changes in enthalpy of the given reactions. When you add the two, you get the reaction 2CO plus C plus O2, which goes to CO2 plus CO2 plus C, and then you simplify it by canceling terms on both sides, both times C, and then adding like terms on the same side, CO2. When you do that, you just add the delta H's and you get 566 kilojoules. When adding the reactions, you're using Hess's law. Using Hess's law, you can solve for the delta H of the following reaction. You add the two given reactions, cancel out like terms from both sides, and add like terms from the same side, and then add the delta H together, which gives you a final answer of 68 kilojoules. How does the reaction 2NO goes to N2 plus O2 relate with reaction A from above? They are inverses of each other, so the delta H's are also inverses of each other. Andrew Lee is cool.